Hi, welcome back to our third lecture in Chapter 5 of Fundamentals of Inorganic Classes. Chapter 5 deals with the structure and structure property relationships in various glass families. The first two lectures dealt with silicate and aluminosilicate glasses, and then borate and borosilicate glasses. Today, we're going to focus on other families of oxide glasses. And we're going to cover actually a bunch of families of non-silica and non-borate based oxide glasses. So oxide glasses not having silica as a principal component do have significantly less commercial usage compared to silicate glasses, but they still have some very interesting properties. So we're going to have an introduction to some of their structure as part of this lecture today. We're going to cover introductions to phosphate glasses. Phosphate glasses are used as laser host materials, vanadate glasses, which are used as low temperature glasses, aluminate glasses that have interesting mechanical properties, and germanate glasses that have a high refractive index. So let's start with phosphate glasses. Phosphorus pentoxide is P2O5, and P2O5 by itself is actually a really nice glass former. The basic structural unit for a phosphate glass is the phosphate tetrahedron. So this is a phosphorus cation here with 4 oxygens at the corners of the tetrahedron. The main difference between a phosphate tetrahedron and a silicate tetrahedron is that with the phosphate unit, only 3 of those oxygens are bridging oxygens. And the 4th oxygen is actually doubly bonded to the phosphorus at the center of the tetrahedron. And this is because the phosphorus cation has a +5 charge, and this double bond is necessary to maintain the charge balance with 4 oxygens. So 3 of the oxygens are singly bonded and are therefore providing bridging bonds to the neighboring phosphate tetrahedral units. And then the 4th one, this doubly bonded oxygen, is known as a terminal oxygen. Structurally, this behaves in a very similar fashion as non-bridging oxygens that we saw in silicate glasses and borate glasses. The difference is that this terminal oxygen doesn't need any modifier to kind of terminate the bond there, just because of its double bond to phosphorus. There's no additional bond that provides any type of bridge here. So do these phosphate tetrahedra obey Zachariason's rules? In fact, they do, because we are forming a tetrahedral unit, and at least 3 corners of the tetrahedra are shared. And so that satisfies Zachariason's rules. And when we start to add modifiers, then we create non-bridging oxygens on these phosphate units. And so we go from Q3 to Q2 species, Q1 and Q0. And of course, the glass forming ability becomes worse as we get to lower and lower Q speciation, because we're no longer satisfying Zachariason's rules if only 2 of the oxygens are bridging oxygens, or 1 or 0. The key thing to know about phosphate glass structure is that even though we start with a tetrahedral structure here, we're starting with Q3 rather than Q4 units because of this terminal oxygen. If we look at some of the speciation in phosphate classes, the plot on the left here shows the fraction of bridging oxygen over non-bridging oxygen as a function of mole fraction of sodium oxide, which is the modifier in this case, as it's being added. And you can see that we start off with about 1.5 bridging oxygen for every non-bridging oxygen, because that terminal oxygen is being included here as a non-bridging oxygen. And then as the modifier is added to the system, there is a linear decrease in this fraction as bridging oxygens convert to non-bridging oxygen. And if we express that in terms of the Q speciation of the phosphate units, on this right-hand plot, we can see that with zero modifier content, that the phosphate glass starts off with 100% of Q3 tetrahedra, and then as modifiers are added, the Q3 tetrahedra convert to Q2 tetrahedra. So the connectivity of the glass network is decreasing. What are some of the applications of phosphate glasses? Phosphate glasses have actually very high solubility of rare earth oxides. Rare earth oxides are used for fluorescence, they're used for laser amplification, and so they can be used as laser host materials. And because of the ability of phosphate glasses to have higher concentrations of rare earth oxides compared to silicate glasses, they make really effective laser host materials. Phosphate glasses can also be bioactive. For example, there are phosphate-based glass powders included in some toothpaste, such as this Sensodyne Repair and Protect with Novamin. And these glasses are able to bond to the enamel in your teeth, and especially where you have exposed roots, there are these tubules in your tooth structure, and that can lead to high dental hypersensitivity. So you can feel pain on there, especially if it's subjected to extreme temperatures, like something very hot or something very cold. And one of the ways to treat dentin hypersensitivity is through toothpaste like this that has ground up phosphate glass powders in it that will react with the enamel of your teeth and form a mineral called hydroxyapatite, which is a calcium phosphate mineral. Your enamel is naturally made out of that, and so this actually helps you to rebuild the enamel on your teeth and repair these exposed tubules to help reduce dentin hypersensitivity. And phosphate-based glasses are also used for other wound healing types of applications for hard tissue repair. Now, vanadate glasses they start off with a very similar structural unit as phosphate glasses. So vanadate is V2O5. Vanadium is a 5+ cation. And because of the 5+ cation, it can start off with this initial unit of the VO4 tetrahedron with 3 bridging oxygens and 1 doubly bonded terminal oxygen. This is exactly the same as in phosphate glasses, but in vanadate glasses, there's also the option of vanadium to have 5 bridging oxygens. So instead of having a tetrahedral structure, it can be bonded to 5 different oxygens. And in that case, all of those oxygens are singly bonded to the central vanadium, and all 5 of them happen to be bridging oxygens. So when we start off with V2O5 glass, there's a mixing of these Q3 units and the Q5 units. Only the Q3 units are actually consistent with Zachariason's rules because Zachariason specifies that the coordination of oxygen around the cation should be small, either 3 or 4. And in the case of this VO5 unit, it's pushing it too high, so it's a bit higher. As a result, vanadate glasses tend not to be as stable as phosphate glasses. If we look at the average vanadium oxygen coordination number for pure vanadate glasses, the average coordination is about 4.4, meaning that there's about 40% of the tetrahedral vanadate structures, about 40% of the 5 coordinated structures and about 60% of the tetrahedral structures to get an average coordination of 4.4. You can see some of the structure sketched out here where there is a VO4 unit and a VO5 unit, and there'd be a mixing of these different types of polytopes in the glass network where the VO4 units and the VO5 units can be bonded together through corner sharing as specified by Zachariason. But as modifiers are added, non-bridging oxygens start to form. Those non-bridging oxygens are forming on the VO4 units, and we're also losing the concentration of VO5 units as those non-bridging oxygens form on the VO4 units. And so the average coordination number between the vanadium and the oxygen is decreasing as modifier oxides are added. Two of the main applications of vanadate glasses are, first of all, low melting temperature glasses for sealing. So you can see that these glasses are actually softening at rather low temperatures in the 200s degrees C, where you can already see this softening type of behavior. So vanadate glasses can be good for low temperature sealing. You can also see that these vanadate glasses are black in color because they are absorbing light in the visible spectrum. They are actually quite good at transmitting light in the infrared. And so they can be used for infrared transmission. And they're also semiconducting glasses, so they can be used for semiconductor applications. So vanadate glasses, because of these properties, can be used for interesting electrical applications because of their semiconducting behavior, optical applications because of their infrared transmission, or sealing applications because of their low melting point and low glass transition temperature. Now we covered aluminosilicate glasses where Al2O3 was incorporated into a silicate glass matrix. Um, Al2O3 on its own does not form a glass. It would be far too unstable. But there is something called a calcium aluminate glass, which can form over a very narrow range of compositions. That narrow range can be seen in this phase diagram here on the right. This shows the calcium oxide alumina phase diagram, where you've got pure calcium oxide here on the left, pure alumina on the right. Neither one of the pure substances can form the glass, but if you mix them in the right ratio, there's kind of a narrow eutectic here, where you've got a mixing of about 64 mole percent calcium oxide and 36 mole percent of alumina. Um, this actually minimizes the liquidus temperature in this binary phase diagram. The liquidus temperature is down to around 1400 or so. And you can actually make moderately stable glasses over this narrow range close to the eutectic temperature, where basically the calcium can act to stabilize the alumina and tetrahedral configuration and also provide some bridging bonds between neighboring alumina units. This is what calcium aluminate glass looks like. It can be made a little bit clearer than this, but it can also have kind of an off transparent color. Um, they do exhibit some transparency in the near infrared, so they're interesting from an optical point of view. But what's most interesting about aluminate glasses is that they've got higher elastic moduli and higher hardness compared to most other silicate glasses. That being said, they're not really in use that much because even though you can make these glasses, they do um, tend to have some surface crystallization, and their viscosity curves are very steep, meaning that they start off very fluid, and then as you cool them, they become rigid quite rapidly. So it's difficult to form these into a particular shape. A more useful family of glasses are the germanate glasses. These are based on GeO2. GeO2 is kind of analogous to SiO2, except the smaller silicon cation is replaced by a larger germanium cation. As I already mentioned when we were discussing fiber optics, one of the useful things about germanate is that it can increase the refractive index of the glass compared to silica. And so you can dope different amounts of germania into silica to create a desired refractive index profile. Now, the right-hand side here shows the structural units in germania. When you start off with just pure GeO2, it's 100% tetrahedral configuration with Q, or in this case, it's labeled as X. 100% of the Q speciation is here in the fourfold coordination with four bridging oxygen. So everything is Q4, just like in pure silica. As you add modifiers to the system, it does create non-bridging oxygens. You get the formation of Q3 and Q2 units. But one of the interesting things in germanate glasses is something called the germanate anomaly, and that you can also create octahedral germanate units upon the initial addition of modifiers. And you can see that with this curve here at the bottom. This starts off with 0% of octahedral germinate. This is the six-fold coordinated germinate units. As you add modifiers, the fraction of octahedral units can increase to about 15% or so, maxing out at around 20% modifier content. And then the number of non-bridging oxygens becomes too high, and that fraction of octahedral germinate units starts to decrease again. The reason for this is it's kind of analogous to what we saw with the borate anomaly and borate classes, where the modifiers can act to charge stabilize the germanium with a different coordination number. But in the case of the germanate anomaly, we're converting from fourfold coordinated tetrahedral germanium to six-fold coordinated octahedral germania. So this requires 2+ charge worth of modifiers, so either 2 alkali modifiers or 1 alkaline earth modifier to charge stabilize this octahedral germinate unit. When this happens, obviously this increases the connectivity of the glass network, and this can lead to anomalous scaling of properties of germinate glasses, analogous to what we saw with the boron anomaly, where viscosity can go up before it goes down. So all of these were playing with different cations, but they were all oxide glasses, just pure oxide glasses. And what we've been discussing is changing the cation from like silica to germania to boron oxide, phosphate, vanadate, and so on. But one other thing that you could do is vary the anion in the glass. For example, it is possible to replace some of the oxygen in oxide glasses with nitrogen. And if you do that, you get what's called an oxynitride glass. And the interesting thing is that whereas oxygen provides bonds to 2 neighboring cations, nitrogen provides bonds to 3 of the neighboring cations. And this increases the bond density in the glass. It also increases the propensity for crystallization if the system is becoming over-constrained. But what's happening is instead of having just one rigid linear bond here and one bond angle for each oxygen, there are 1.5 linear bonds because there's 3 bonds with the nitrogen. Each of the 3 bonds is shared by the 2 neighbors. So it's 3 divided by 2, so 1.5 radial constraints, but then 3 angular constraints as well. And so we're going from a total of 2 constraints per oxygen to we're having 1.5 plus 3, so 4.5 constraints per nitrogen. And so this can enhance some of the mechanical properties of the glass. And in fact, if you've watched Jurassic World, there's a scene where the kids are running away from dinosaurs, or they're in this kind of hamster ball, a sphere of glass, and they remark that it's made out of oxynitride glass to get the higher hardness to give them greater protection from the dinosaurs that are in pursuit of them. And indeed, that's what we can see here, is that if you start off with a pure oxide glass and then start replacing oxygen with nitrogen, the hardness of the glass can increase, and it increases rather dramatically. You can see about a 20 to 25% increase in hardness, depending upon the amount of loading of nitrogen that you can put in. The difficulty is getting the nitrogen into the glass, because if you just batch a nitride material and you melt your glass in an oxygen-containing atmosphere, the glass very much prefers oxygen, and so the nitride would get released as nitrogen gas and be replaced by oxygen from the environment, and you wouldn't actually have an oxynitride glass, you just have an oxide glass. So as a result, oxynitride glasses need to be made in basically a nitrogen atmosphere in order to make sure that that the nitrides are retained inside the oxynitride glass. The other issue is that they are easy to crystallize because they can easily be overconstrained. If we go in the other direction with anions, and instead of replacing the oxygen with something with a greater coordination like nitrogen, you can move in the opposite direction and replace the oxygen with a halide, like fluoride or chloride. The halide only has a single bond to the cation. So, for example, in this fluoride glass, the fluoride ion is just bonded to one of the silicons and not to the other. And so replacing oxygen with a halide is effectively the same thing as replacing a bridging oxygen with a non-bridging oxygen because we're breaking up the connectivity of the network. The difference is this is actually doing a chemical replacement where you've got, instead of a -2 charged oxygen, there's a -1 charged halide. And what that means is that we're breaking up the connectivity of the network, and that's going to lower the modulus of the glass, decrease the viscosity, and so on. So this is an example of an oxyfluoride glass. You can make oxychloride glasses as well. The nasty thing about these glasses is that, again, if you melt it in a regular atmosphere, the glass very much prefers oxygen, and it will release fluoride into the atmosphere and replace it with oxygen. When the fluoride gets released in the atmosphere, it actually forms fluorine gas, F2 gas, and that creates a huge environmental problem because if you breathe in fluorine gas, that's going to react with the water in your nasal passages and in your lungs. The fluorine gas reacting with water produces hydrofluoric acid, and you'd end up with hydrofluoric acid in your nose and in your lungs, which obviously is a very bad thing. So oxyhalide glasses are not fun to deal with. They're actually rather dangerous. So to summarize this lecture, we have covered 4 other types of oxide glasses: phosphate glasses, which consist of tetrahedra with 1 terminal oxygen and 3 bridging oxygens. When you add modifiers to phosphate glasses, that creates more non-bridging oxygens. Vanadate glasses start off with a structure that's very similar to phosphate glasses, but a certain fraction of them are also 5-fold coordinated vanadium. So there's a mixture of Q3 units and Q5 units in vanadate glasses, and then adding modifiers lowers the conductivity of the network by creating non-bridging oxygens. Aluminate glasses have some interesting mechanical properties if you get just the right ratio of alumina and calcium oxide. However, they are quite prone to crystallization and they are difficult to form because of their very steep viscosity curve. Germanate glasses are quite useful as optical glasses. Their structure is similar to that of silica, but they give a higher refractive index because of the larger size. And the difference is when you start to add modifiers, some octahedral germanate units can form. So this gives us a germanate anomaly, which is kind of analogous to the Boyd anomaly. We also have mixed anion glasses. That includes oxynitride glasses, where the incorporation of nitrogen increases the conductivity of the network, and oxyhalide glasses, where the incorporation of halide ions decreases the conductivity of the network. All right, that does it for oxide glasses in Chapter 5. Next time, we are going to give an overview of different families of non-oxide glasses, and that will be the last lecture devoted to Chapter 5. All right, thanks again for watching, everyone. I will see you next time.